Now let's talk about the second derivative. What does the second derivative tell us about a function? The second derivative tells us two things. Like the first derivative, the second derivative tells us also two things. It gives us the concavity intervals. And it also gives us points of inflection. Of course, they go together. So let me give you an example. This is a very well-known function. Can anyone tell me what I'm graphing? Very well known. Can anyone tell us what function is this? No one? Okay. So this is x cubed. And notice what happens here. This function does not have any terms. Doesn't have max and min. No critical numbers. It may have critical numbers, but those critical numbers don't change. The derivative doesn't change sign, so the critical numbers are do not turn into max min. But here's what happens. On this side, the function is opening down. At this point, it changes concavity, opening up. We call this piece concave upward. And this one, concave downward. Okay. Obviously, this point is what we call inflection point. It's where the function changes concavity from opening down to opening up, or vice versa, from opening up to opening down. So how do I determine concavity, and how do I determine the points of inflection? How do I get from the second derivative to knowing concavity and points of inflection? Okay. So when the second derivative is positive, we say that the function holds water, concave up. When the second derivative is negative, the function does not hold water, is concave down. When the second derivative changes sign from positive to negative, there is an inflection point there. When it changes sign from negative to positive, there is an inflection point there. If it doesn't change sign, it does not have a point of inflection. Since we are looking at x cubed, why not start with this? So I'll go back to the function I didn't forget. So we have f of x, which is x cubed. The first derivative, obviously, is 3x squared. And the second derivative is 6x. So what happens here? I can set the first derivative equal to 0, and I will get x equals 0. But you'll see in a moment what happens. So let's create a table for x cubed, f prime, f of x, and the second derivative. So of course it's defined everywhere. I know that at 0, the first derivative is 0. I plug in 0, I also get 0. But can anyone study the sign of 3x squared for us? Because we need to put the sign for 3x squared. What type of function is it? Quadratic. Is it ever negative? No. So therefore 0, 0 is not a point of max min. And we knew that. Okay, the second derivative is also 0 when x is 0, but the second derivative changes sign. On this side is negative. On this side of x is positive. So 0, comma 0 is an inflection point. The function, when the second derivative is negative, the function will open downward. When the second derivative is positive, the function will open upward. And that's exactly what we have. Between negative infinity and 0, the function opens downward. The second derivative is negative. Between 0 and infinity, the function opens upward. So the second derivative is positive. Having this information, I want to go back to finish up our function with part C. So we do have the first derivative. In order to continue and try to find concavity and inflection points, I have to find the second derivative. So let's find the second derivative. 24x plus 6. I set this equal to 0. And I get that x equals negative 6 over 24, or x equals negative 1 over 4. And I have negative 1 over 4 right in here. I put 0 for the second derivative. When I study the sign of such a linear function, I know it has a positive slope. It's coming from negative going to positive. I know that the function has to open downward here and open upward here. I have to plug in negative 1/4 because I have to tell you what the inflection point is, like I did here. Negative 1 comma 6 is a local max. 1/2 comma negative 0.75 is local min. I cannot just say there is an inflection point when x is this. I have to find the y value. So I'll go back to the calculator, and that is negative 0.25. So 4 parentheses negative 0.25 to the third power plus 3 multiplied by, I don't need to put negative, so it's 0.25 squared. Then minus becomes plus 6 times 0.25, and then plus 1. And I got 2.625. So this is 2.625, and this is the inflection point. So again, the inflection point is negative 1/4 comma 2.625. It's where the function changes concavity. Again, you don't have to put that in writing on a test. For me, because if you present a table or this table, it's very clear to me that you are saying the function is concave down between negative infinity and negative 1/4. And the function is concave up between negative 1/4 and infinity. And this is it. We answered all questions. Any questions? Let me stop for a second and let me know. Any questions? Any questions on the table? Anything? Okay, I don't hear anything, so I'll let you choose the next problem. We'll go through the same steps, and then I will explain, and I'll come back to this function, because I want to explain the second derivative test. Questions, please. Would you like to choose the next problem? Is anyone there? Did you go for a walk?
We're here, sir. We are out here. We're here. Yeah.
So please don't go for a walk. We need to do this, please. Okay, good. So any preference, anything? Would you like to choose? You want me to choose?
Yeah, you always pick the best questions if you ask me.
Well, if you ask me, you always get the best questions. Anything. Was it clear how we determined the increasing, decreasing, how we determined concavity, inflection points, max, min, local max, local min? Okay. Would you like to choose something else to work on?
What page are we on?
We are on page 298, problems 9 through 18. And of course, I would like us to, this is a good summary of all the information that is given so we can come up with a function. So we will choose any problem you want from here as well. But I think we should work on at least one more of this type.
Lucky number 13.
It is 13. That's your sine x plus cosine x. Unbelievable. She's torturing us. Okay. So 298, we have f of x, sine x plus cosine x. Are they giving us anything in there? Oh, thank you. At least that. They're not torturing us everywhere. There's just between 0 and 2 pi. Okay. Sorry about that. I was just kidding, of course. Okay, so let's get it started. Only between 0 and 2 pi. F prime of x, f of x, and double prime. First question, again, it's asking us to find local max, local increasing, decreasing, local max, local min, and concavity inflection points. Basically, this is the entire, almost the entire preparation for graphing. That's what we really need. Okay. So I will plug in 0 to see at the end point. Sine 0 is 0, cosine 0 is 1. Again, the same thing here is because it's the same point. Sine 2 pi is 0, cosine 2 pi is 1. Then I'll continue with the first derivative, which is cosine x minus sine x. No critical numbers coming from f prime being undefined. But we have to solve the equation f prime of x equals 0. So when we write cosine x minus sine x equals 0, in such a situation, what we need to do is divide both sides by cosine. When I divide both sides by cosine, I have to write that cosine cannot be 0. Well, it's not possible. If both cosine and sine are 0, then the answer will not be 0. Then I will not have a solution because there is no angle for which cosine and sine are both 0. So, but anyway, I divide by cosine. I have to state that. And when I divide, I get 1. I get minus tangent x equals 0. Or tangent x equals 1. On the unit circle, tangent is 1 for this angle as well as for this angle. Which angle has tangent 1? Pi over 4. 1, 2, 3, 4, 5. So this must be 5 pi over 4. 2 pi over 4 here, 2 pi over 4 here, and 1 here. 1, 2, 3, 4, 5. So x equals pi over 4. X equals 5 pi over 4. I put them in the table. These are the critical numbers. So pi over 4. I'm just going to put them, so this is pi over 2. I don't need it. And pi. And this is 3 pi over 2. So that I find the correct spot for pi over 4 right here in the middle. And 5 pi over 4 is between pi and 3 pi over 2, right here. 5 pi over 4. Critical numbers, that's where the first derivative is 0. Okay. Next, I have to study the sign of the first derivative. Well, in this case, I'm going to plug in 0 for this piece, positive and 0. For this piece, I'm going to plug in pi over 2. So this is 0 and this is 1, minus 1. Even if I plug in pi, this will be still negative 1 because this is 0. Doesn't matter. And here when I plug in, let's say 2 pi on this side, this is positive and this is 0, so positive. Not too bad. I have to find this number and I have to find this number, because I have to give you the local max, local min. So when I plug in pi over 4 in the function, I'll have the square root of 2 plus the square root of 2 is 2 the square root of 2 over 2, which is the square root of 2. When I plug in 5 pi over 4, both are negative. And both are going to be negative the square root of 2 over 2 minus the square root of 2 over 2. So this is negative the square root of 2. Not too bad at all. Okay, now I want to make sense of these two. Make sure they work well together. Ready? From 1 to the square root of 2, what does the function do? Well, I'm assuming you're saying increasing. Is that supported by the sign of the first derivative? Yes. From the square root of 2 to negative the square root of 2, the function is decreasing. Is that supported by the sign of the first derivative? Yes. From negative the square root of 2 to 1, yes, it's increasing. So it appears that they all work smoothly together. Okay, now I have to look at the second derivative. So the second derivative, cosine prime, negative sine x, and then minus cosine x. So I have negative sine x minus cosine x equals 0. Again, I divide by cosine x, which is not 0, and I get negative tangent x minus 1 equals 0. And I get tangent x eventually after I move this to the other side and divide by negative 1. Okay, well, in that case, I have this now. This is one angle, and this is the other. 1, 2, 3. So x equals 3 pi over 4. And of course 7 pi over 4. 1, 2, 3, 4, 5, 6, 7. So 7 pi over 4. Okay. So it's good that I put my quadrants in there. So 3 pi over 4. 0. 7 pi over 4. 0. Okay, now I have to study the sign of the second derivative to fill it in here and decide concave up, down, whatever. Okay, so before that I have to plug in this in here and here. So with 3 pi over 4, sine is positive, but cosine is negative. So this will be 0. And with 7 pi over 4, cosine will be positive, but sine will be negative, and there's still 0. Good. So I will plug in 0. A 0, this is 0, this is 1 with minus in front. I will plug in 5 pi over pi. I want to plug in pi. So when I plug in pi, this is 0, this is negative 1, so it's positive. Finally, I plug in 2 pi. This is 0, this is 1 with minus. This is all I need you to create. I don't need you to write separate. The function is increasing between 0 and pi over 4. Union 5 pi over 4 and 2 pi. I don't need you to do that. I see it. You don't have to write that the function is decreasing between pi over 4 and 5 pi over 4. I see it. It's clear. You already put the symbols, right? It's fine. I know that you're saying to me that the function is concave down between 0 and 3 pi over 4, union 7 pi over 4, 2 pi. It's very clear to me you're telling me that the function is concave up between 3 pi over 4 and 7 pi over 4. And writing here that pi over 4 comma the square root of 2 is a local max, that's good enough for me. 3 pi over 4 comma 0 is an inflection point, very clear. 3 pi over 4 comma 0 is an inflection point. 5 pi over 4 comma this is definitely a local min. You don't have to write it separate. I can see it here very clearly. And 7 pi over 4 comma 0 is definitely an inflection point. So it's an IP. All the information is in the table. Only if I summarize it in a table, not necessarily this one if you don't like it, I will be able to, in this section, graph this whole thing with no calculator. As long as the information is summarized.